Our guest speaker is Travis, and he's going to be talking about making Python fast behind the scene, looking at why it's an interpreted language which dominates data science, machine learning, and artificial intelligence. So, the Microsoft Excel UrBizEdge is a registered Microsoft Excel financial modeling, business intelligence, data analysis, and enterprise solution firm in Nigeria. They're also the developers of the Nigeria Stock Analysis Dashboard and the Nigeria Financial Market Analysis Tool, which is on the Microsoft Office store as well. Okay, so they also offer online classes and physical classes as well. So I'll put the website in the chat description. Okay, so today our guest speaker is Travis, and is the CEO of OpenTeams, Growing Insights. It's also the foundation of Anaconda, NumPy, Python, SciPy. He's also the scientific computing developer and administrator with over years of experience and has completed project for Fortune 50 companies. He has also built a lot of successful businesses based on open source, while also improving how programs are generally read and seen. He has also built softwares like everybody is very familiar with NumPy, which foundation of a lot of scientific Python, and SciPy, which is the foundation of scientific Python. And these tools have helped data analysts, data scientists, engineers to make it easier for them to deal with data and take this the dominant expertise and how to utilize computer in general as well. And he also enjoys customer-facing relationship and partnership building, simplifying complex ideas with programming, product development, and doing everything related to building a software business. Hello,
So,
Travis.
Travis, it's a huge pleasure to have
Hello.
you. We are going to hand over to you. So he's going to stop sharing his screen, and then
I just started to learn Linux and learned about open source, and I started to contribute. So I'm on slide, go down a couple of slides at this point, slide 3. I can see the slides. Maybe others can too. Yeah, so I led to Python when I was at the Mayo Clinic studying science. Elastography from MRI and ultrasound, we could watch waves propagating through the body, and then I could try to invert it using that tensor equation above. So I wanted to figure out how could I measure the stiffness, so that CIJKL tensor, using the measurements of data. I started to use Python to do that. And why did I start using Python? I could write in C, but when I was writing in C, I had to chase pointers, had to think about all the syntax. When I wrote in Python, it was easy. I could just think about the algorithm I was doing, and it was iterative, and I could incrementally add to it. So move on, next slide. After Mayo Clinic, I continued in the academic circles, still working on what at that point was SciPy. I started at Mayo Clinic just to release a bunch of packages, optimization libraries, integration libraries. These were all pretty hard to install. Back then, you had to kind of compile it yourself until a high school student named Robert Kern helped me start building binaries for Windows. Before then, you had a website, people downloaded a set of source code, they compiled it and then installed it. And all these things were extending Python to do essentially to do the calculations and the analysis that I needed. At BYU, I was studying a particular scanning approach, electrical impedance imaging, scanning impedance imaging. But I kept developing SciPy. Actually, at BYU is where I ended up writing NumPy as well, really to make more cohesive the SciPy community. I wanted the NumPy community had started a fork and factor into NumArray and numeric, and so I basically wanted to bring them back together, and so that's why I wrote NumPy. And that was in 2005, 2006. Move on. Next slide. So I've been doing this a while. Basically, I started at the Mayo Clinic. By 2006, I wrote NumPy. At that point, I'd become really addicted to open source kind of collaboration. I really loved interacting with people all over the world who would share ideas and hints and code. Got to some conferences at that point and met people who I was collaborating with. Not all the people I was collaborating with. Many people I'm collaborating with I've never met, but most of them I have at this point, which is awesome. But I was finding myself more and more writing code, less and less writing papers and algorithms, and doing analysis and research grants. And so then I left academia and started to pursue a career in business. And that's where my love of trying to figure out how to make business work happened too. I actually learned economics, trying to understand how to make open source work. And I studied a lot of economic literature and learned essentially what it is that makes, how do people become well off? How do societies become better? What are the principles of actually human organization that make that successful over the years? And there's a lot people have learned. So I got really excited about that. One of the key things I learned was actually entrepreneurship is critical. Having people create and then businesses and create solutions that others can buy is a really key step to prosperity and to growth. And so I got, now I have two loves. I had open source communities and I had entrepreneurship I wanted to pursue. And so for the past 15 years, I've been pursuing both of those interests to create companies that help open source communities. So I've been doing that ever since, and along the way have kind of been participating in the emergence of pandas, emergence of scikit-learn, and then we started a company, Anaconda, in 2012 that produced Conda, that essentially became a way to how to install all this stuff. Wrote Numba, which is a compiler. Essentially, that's been the journey, and then still on that journey. Started Quansight in 2008 and OpenTeams in 2019, and I got another idea called PharaohSS that I'm really excited about, but won't have time to talk about today. But these are, open source and community collaboration has been my life. So I wanted to kind of skip on now to talk about kind of the SciPy and NumPy impact and kind of why it's driven me this direction. Keep moving. Next slide, please. So SciPy and NumPy, of course, to be successful, it's because thousands of people have contributed to them. I was really excited and really did a lot of work actually to get these started, and ended up having to do things not really clear on where that would go. Very much a pioneer. Very much I didn't know whether SciPy would be successful. Didn't know whether NumPy would be successful. I just sort of put my all into it, and then by doing that, I attracted many other smart people to join me, and at this point, thousands have not only joined me in SciPy and NumPy, but also in other libraries that use these libraries. And so building the ecosystem around it. And that's been really essential and had a huge impact. Actually, it's much beyond my expectations. I knew we'd be able to solve some problems. I didn't realize we'd be able to kind of support, a fourth of all science in the world. And this is based on, how do you measure that? Well, if you look at the papers published on arXiv and look at the PDF files, you can see kind of how they're generated, and about a fourth of them use Matplotlib, which is a plotting tool in the Python ecosystem. But it's had a massive impact. So now, these days, what I do to kind of join these two loves of entrepreneurship and open source, move on, please. I'll just say move, and then if you just flip when I say that. No, move, go back. Sorry. Now I find people, tech visionaries, founders, investors. I try to connect the dots between people that are creative and creating solutions and want to build companies that support open source communities, and then those open source communities themselves. So this is an example of many of the things. Anaconda was the first, also started NumFOCUS, being led now with a bunch of good people. Quansight Labs, OpenTeams. OpenTeams has OpenTeams Global, OpenTeams Incubator. These are all things we're doing right now. Always excited to meet people, always excited to meet entrepreneurs, people who want to create and build. So it's a pleasure to meet everybody. OpenTeams Global, in fact, is building an open source professional network to find people all over the world who want to be able to make open source a career, and they'll connect to the opportunities that arise because of that passion. So very excited about the work we're doing to try to grow open source communities through the individuals that make that possible. And it really is individuals that have made possible, move on please, that have made possible Python's growth in science. So I want to talk now about Python and why it's cool, and how in the world did this slow language become essentially the cornerstone of science, and then lately artificial intelligence, machine learning, even GPU computation. So it's actually probably surprises a lot of people. I know a lot of people at Intel and Microsoft and Google, even some degree, have been surprised. I think I've had relationships with Microsoft for many years, but they took a long time before they figured out why Python was actually really critical. Effectively, the community around Python, all the scientific programmers who are using it, kind of forced the rest of the world to take a look at it. Jeff Dean created TensorFlow at Google, very big guy at Google. Sumit wrote PyTorch at Facebook, or Meta, now Meta. These libraries are dominating AI and ML. When they came out, they were written not in Python, they were written in C++. And effectively what happened is they released these libraries and everybody said, where's your Python interface? So because of the work we've been doing for the past 20 years before that, before 2015, 2014, then when they started to release their tools, everybody said, you got to have Python interfaces. And so that led them all to kind of go, oh, okay, we got to use Python. And so I've had a chance to meet these people doing these amazing work, and a lot of work, actually, millions and hundreds of millions of dollars spent on these very large scale deep learning networks that are much bigger than the efforts we put in. Although I think over time, with the number of people, all of the rest of us in the open source community-driven community of NumPy, SciPy, Pandas, scikit-learn, matplotlib, and the rest, we haven't had a lot of budget typically. We've just had a lot of community and a lot of passion, and we've been able to create a lot with that. These days, there's a little bit more budget coming our way from a few grants and a few folks, and that's exciting and really awesome. And let's just bring in more people in the community. But why is it? Why did Python come to dominate this space? It's a slow language. It's interpreted. Well, I'll tell you some of the things I really love about Python. One, it's expressive. You can write things very quickly in Python. It fits your head. It's a shallow language. When you write, it's often said when you write algorithms in Python, it's executable pseudocode. One big part of that is they have dynamic typing. Other languages, when you're forced to write types and you're a domain expert, that means somebody who wants to think about the science or the finance or the something else besides programming, having to worry about types really gets in your way. Even though types are really important for you to distinguish and essentially dispatch the right machine code for what you're trying to do, it's in the way. And getting rid of that syntax for types, which Python enables through dynamic typing, really helps communicate more effectively. Then, of course, the big thing about Python these days especially is the amazing ecosystem, the great libraries. Now, when I came to Python, it was 1997. And at the time, there was an ecosystem. The standard library had a lot of stuff in it. What I liked about it is it wasn't all the libraries there are today, certainly. But what I liked about it is I could tell that, one, people who came to Python were sincere and really cool people, and they were smart and intelligent. And two, I saw the future. I saw a future in Python. I saw that, there's a bunch of people to be gathered around this watering hole, this ecosystem, and together we can create something amazing. And that's what's happened over the past 22 years. This amazing ecosystem has been built up. You have great interactive development these days, from Visual Studio to Jupyter Ecosystem. Fantastic. Python's always had a REPL, they call it, a read-eval print loop REPL. But the IPython, interactive Python, which came out in 2000, 2001, even better, very expressive, very easy to iterate and code with Python. I often tell people that the key to innovation is iteration. If you want to innovate, yeah, it takes some real brilliance and takes capability, but you can kind of predict the speed of innovation by understanding the speed of iteration of a company, of a process, of an organization, a group of people. Because no matter who we are, all of us make mistakes, and we have to keep fixing our mistakes. The whole key to progress is quick fixes. Do something, be bold, take a leap, and then quickly change in order to become better. That's basically, if I could summarize life quickly, I think that would be it. Take bold initiative, but be open to change. Constantly recognize you have to get better and do things better. Python enables that. Enables you to do that easily and quickly. So the fact that Python fits your brain enables you to build something quickly. And then maybe because of those early days, the community has stayed amazing. Many people have said they came for the language and stayed with the community. I've met so many wonderful people all throughout the world. It seems to pull out the best in us and bring people together in a way that is really healing and amazing, especially in a world that seems crazy. I've loved my interaction with Pythonistas and people in the Python community who are focused on making things better for each other and for everybody else. Let's move on. Next slide. So this is just a reminder to use interactive Python whenever you can. Interact with your code and your data. The whole key to making effective use of Python is to essentially iterate quickly with the code you're writing. Get your hands around the data. I like to say, import things, start to play with it, bring things into a pandas data frame, bring things into a NumPy array, bring things into a dictionary, start looking at the data, understanding how transformations affect your data. The faster you can do that, the faster you make progress. And now these days you can interact even with simple GUIs, it's very straightforward to build little graphical user interfaces, even from Jupyter Notebook, where you can build with things like Panel that lets you create applications very, very quickly, web applications. And then, of course, there's PyScript that has emerged to make it even easier for the Python space to write web applications. Very excited about that development by my friends over at Anaconda, my co-founder, Peter, over there. Go to the next slide, 10. Next slide, please. Okay, yes, dynamic typing. I'm looking at the wrong screen. Python, it optimizes the speed of development. That's the key. A lot of articles written about this, but the whole point, people say Python is slow, quote unquote, maybe, but it's actually fast to develop. And that's much more important because people, the time of individuals, of people is more valuable than the time of machines, which you can replicate pretty quickly. You can just scale out machines. So the dynamic typing means you just start coding. The expressive and simple syntax means you can express a lot of ideas quickly. The built-in data structures, dictionaries, lists, strings, and the extensive numbers means you can quickly write stuff. One of the favorite things I do with people that are new to programming is send them to Project Euler. Project Euler is just a set of tools for kind of algorithmic development, and it's just a way to start thinking logically about solving problems. You go there, and man, some of those are they really hard in a language besides Python. In Python, they're really easy sometimes, especially with the long integers of Python, where you can have integers of any length. That becomes super helpful. The improvements over the years, I think they really aid writing and reading code. If you look at Guido von Rossum, the big thing he's always demanded is that Python be easy to read, that easy to teach about. So he started Python as a teaching language, trying to help people understand programming. And so he wanted it accessible. That push to make it accessible to many folks has meant that it's accessible to people that are what I call occasional programmers. Like I consider myself, I did originally, now I'm more of still an occasional programmer. I cared about science. Now I care about entrepreneurship. I don't program all the time every day. So Python is really helpful because it helps. You don't have to keep all this syntax in your head. You don't have to keep all this stuff in your head. You can just read it, quickly iterate, get to a point. You can share it with others. It's fantastic for people just trying to share code that does something they otherwise want to think about something else. And the world's a big place. There's lots of stuff to think about. Next slide. So why is Python slow? Nope, too many. Go back. You skipped too many slides. Back, one more slide. There we go. So why is Python slow? And then we'll go on and talk a little about how do we make it fast? How does Python become fast? Because if everything's slow, it wouldn't have dominated. If things take too long, then it wouldn't take over machine learning. You have GPUs if you want to take advantage of it, wouldn't have happened. So why is Python slow? Well, it's slow because of the dynamic typing. Dynamic typing makes it awesome, but because all the variables are typed, you don't know what they are. And so the machine can't optimize code for that variable. So it's a kind of a trade-off. You basically have the advantage, you can execute anything at any time, but the disadvantage is, well, that has to make a dispatch, has to make a decision. There's an if statement there. The other aspect is all the variables, all data, so an integer or a floating point number, it's boxed, meaning that you don't just have the raw bits that represent a number 42. You have a number 42 along with a bunch of other information like, oh, what type is that? Oh, how many references do I have to that 42? Well, reference counting. I mean, if you look at a Python object, you can go look at the C code. It's pretty cool because it's open source. You can go look and see, okay, how does a Python variable translate to what's in memory, what the machine actually references? And you'll see, oh, there's the pointer to the data itself. And then here is the header. Here's the information about the type. Here's a pointer to the number of references that are here. You can see that's a basic Python variable. Then it's also interpreted. So you don't actually, a machine reads machine code, means it has the internal processor of a machine has instructions that it executes, and then registers it pulls from, and then some of those instructions pull data from memory into registers and do things like add and subtract. That's not what's running when you run a Python code. What's running when you run Python code is you have compiled the Python syntax you've written to a bytecode. That bytecode is things like pop from the stack, add two numbers, or add the top two variables of the stack, or make a function call using the top three. Anyway, there's various instructions. Those instructions they're called the bytecode instructions. And every version of Python released, you can look at what the bytecode is for that version. It's actually really nice in Python. You can explore it and express it. There's code tools let you do that. Oh, I can compile the code and look at the bytecode that's produced and do something with it. But what it is, it's a big case statement. That's what the virtual machine is. It's a big switch statement in a for loop, in a loop. While loop with a switch statement that basically just does different things based on the bytecode that it encounters. That's what's running. So that's it runs that all the time. That's not the same as running your matrix multiply algorithm. So the other aspect of Python that makes it slow is a single threaded. The virtual machine can only run in one thread. So especially these days when a lot of speed up with the end of Moore's law and the fact that processors aren't getting faster, but we're making more of them and putting them together in tighter bundles, that means to get fast execution, you really have to run on multiple cores. And so how do you do that? Because Python itself doesn't do that. Python itself is still single-threaded. That's the vaunted global interpreter lock, or GIL, you'll read about online. So move to the next slide, please. So how do you make Python fast? Okay, I'm not going to talk about what the core developers are doing. You'll read about that. You can read about, oh, Python 3.11 is faster because the core developers and they're doing some cool work. It's really interesting, actually, what they're doing. There's people that talk about that. They're getting you can get 25% speed ups, maybe, if they're hopeful. That's cool. It's very fascinating. It's not doing that wouldn't have made Python dominate science and AI. That's not what we're talking about. It's something from my perspective, it's kind of irrelevant almost. Like, okay, that's cute, but doesn't help really. What I care about, I wanted to make 2,000 or 2x to 1,000x speed ups. I care about really big speed ups because Python itself, if you try to run on a million numbers, a for loop in Python that's doing an addition of two floats in Python, that's way too slow, like way too slow. You'll never train a neural net if the algorithm itself is going through the interpreter loop, right? So that's never going to happen. It never has happened. That's not what we're talking about when we say make Python fast. What we're talking about is actually bypassing the interpreter and calling native machine code, and preferably code that somebody else has written, not you, because no matter who you are, and me included, I'll go to the front of the line here. Actually, no matter who you are, somebody else wrote faster code to do something. Now, maybe if you're lucky, you may have written the fastest version of some small piece of code, but together we get the best possible fast code. That's the amazing part of open source. It really taps in to the intellectual capability of the entire planet. And not only the entire planet alive today, but the entire planet that's been living for the past 100 years. So amazing, amazing, amazing. And we need to take advantage of that. And that's really the key, because of Python CPython in particular can be extended with other code. That's the key to its success. That's how it became fast, is that extension capability. Like I said, when I was a young person, I started extending Python. I said, oh, here's Python. It's really cool. I like to write it. But, oh, I need to actually call out to an integration library. I need to integrate my function. Integration algorithms. How do you do that? Well, I've taken a numeric class. I can do Romberg integration. I can do trapezoid integration. Maybe there's some clever approaches. But then I looked around and I saw, oh, there's actually this Fortran code called quadrature. QuadPack exists, and that was written by somebody else smarter than me, who at least had more experience than I had writing integration libraries. So that was cool. I went and grabbed QuadPack, which is a Fortran library, compiled it, and then put bindings linked to it from Python. So a Python user could call quad, essentially an integrate function that went out to that code and ran it. And that was in native code. Now there was some tricky stuff there because I had to actually have that code call back to a Python code, which is the code to be integrated. And there's some challenges there, but some interesting opportunities there too that emerged later on. But that was the whole key. So I was out there just extending Python to reach all this cool stuff that was in I found a website that had a bunch of old Fortran code it linked to that did really cool stuff: integration, ordinary differential equation integration, optimization libraries. And so that was the beginning of SciPy. That was the beginning of my journey, was actually trying to figure out just how to glue great code that already existed somewhere else and make that available to Python users. So, you know, it's a lot of people go, oh, cool, all these great algorithms that you helped create. And I said, I didn't create most of those. There may be one or two that I'm like, oh yeah, I did something cool there. But of the hundreds of libraries that I brought into Python, it was because of other code. And there's just this great ability to extend Python. So that really is the key. The extensibility of Python was the key. Let's make the next step. So what does that mean? So let's go into more detail then. How do you make Python fast? I'll step back a bit and kind of tell a story here. And I had some code to share on a screen. I can maybe put it up online somewhere. It's not exciting code, but it was fun to do it again. Only took me about a half an hour to put the examples together. But I put an example together with Fibonacci numbers and prime numbers. And just to show kind of the step, how you go from, how do you make code fast is, one, write a better algorithm, right? A lot of times you can speed up a bad algorithm and you'll still be slower than Python with a fast algorithm. And that's actually a story told by my friend Fernando Perez, who wrote IPython and Jupyter Notebook and Jupyter Project. He tells a story when he was a grad student. He and I have been friends for years, and he was adopted Python as a grad student just like I did. And he was in a lab, and everybody else was using Fortran. Fortran's this famously fast code compiler. As folks have said, you know, the lives of hundreds of grad students are buried in the compiler, in Fortran compilers, speeding them up. But the professor loved Fortran because it's produced fast code for scientific code bases. It was the king. It still pretty much is, actually. He was saying, you got to use Fortran. And Fernando said, oh, do I have to use Fortran? Can I use Python? He said, well, that's fine. You can use Python. So Fernando used Python. They were doing this coding exercise with the class, about 4 weeks of work. Fernando had the fastest code. Fernando produced a solution with Python that was faster than anybody else's Fortran solution. So you can build faster code with Python. Of course, then you look at the details. Well, how did he do that? Well, because he iterated a bunch of times. He was able to go through not just the first algorithm he could think of, but several other versions of the algorithm, because he could get it done so quickly, because Python made his speed of iteration so quick. So that's how he ended up writing a faster algorithm, because he wrote a faster version, because he wrote a better algorithm. And so I just showed an example of Fibonacci. You know, Fibonacci, you can do it recursively, just do it brain dead perhaps, or maybe a little clever, but it's just straight up recursion. But Fibonacci has a double recursion. It's the sum of the previous two answers. That double recursion starts to build up a lot of expense very quickly as you get down the line. And there's other ways to think about that. Well, you could actually do a tail recursion, invert that, not recurse. You could just, you know, at the very end, just store two numbers. Finally, there's actually a formula for the nth version of a Fibonacci sequence. That's a fun exercise. If you haven't done that, you can find it using a number of approaches. But that formula gives you just compute the value. That would be the best algorithm to use to find the Fibonacci number. That's for an example. Then primes, you know, computing primes. If you wanted to compute all the primes less than 1,000, for example, well, there's a sieve erasthonist. You know, if you figure that out and learn how to do that, then it's actually much faster to use that algorithm. So number one, use a better algorithm. And then my caveat to that is preferably written by somebody else. Use a better algorithm, preferably somebody else wrote. Not that it's not fun to create better algorithms, and it is, but man, there's a lot of cool stuff that gets built, and it takes a lot of effort to do so, and you're not going to be able to do everything you want to do to speed up your code, to speed up your problem by trying to solve all those problems yourself. Go grab somebody else's stuff. That's the power and the value of human cooperation, and it really shines here. So you know, use a better algorithm. Hopefully somebody else is using it, and you just call it. Then Python is just this glue. Then Python becomes a scripting glue between calls to fast code that other people have already built a bridge to. That code could do something like, you know, multiply matrices on, you know, thousands of matrices on a GPU. You're calling it from Python. You don't know that it's going off and now you're not worried about single threaded, because the GPU has thousands of threads it's running and it instantly computes. Or it's thousands of CPU threads it's calling. So that's the essence of how we've made Python fast over the years, is by basically using Python as a bridge. Let's move to the next. I have just a few examples here of NumPy, for example. So go on, click next. So NumPy, I don't know how many people here know NumPy. I know this is a group of folks that do a lot of things. I know there's some people who know NumPy. See a couple of names here, people actually help work on NumPy. So I know there's probably a wide variety, but I wanted to kind of give a flavor of what does this mean. So NumPy, what it does, it adds an array object, an array of native data. So in Python, a list in Python, every object is a Python object. So a list object is a collection of other Python objects, but each number in there has the extra reference count, the extra type information. You replicate that for element in the list. Now, if you're only having 1,000, maybe even 10,000 elements, not too big of a deal, actually. Python's not slow. If you're dealing with that level, it's usually fast enough. But if you're doing 10,000 elements, your sizes start to grow, then you want to start not paying the cost of having all that extra stuff. So NumPy arrays just collect a bunch of data, say floats or integers or complex numbers, into a single chunk of data. And this is an example of how you would sort of not use NumPy. You'd maybe use a list comprehension and call imagine you had a function file like this that implemented a sync function or a step function. Notice it has an if statement and just a simple function that returns a value for a given x. One is this sine over x, sine of x over x function, and then the other is this step function. So that works fine. You can build a list of computations, and if you're talking about 10,000 elements, that's really fine. It's no big deal. I wouldn't call that bad. It's a reasonable solution. Go to the next slide. But if you start getting more than 10,000, you want to do something a little different. So essentially, you want to vectorize. Vectorize is this idea of I want to take a function and apply that to every element of the NumPy array. So I have a big array of data now. It's all the same elements, all the floats, and now there's no more extra type information. There's just type information about the array and a reference counting on the array, but not every individual element. And so then I need to be able to apply functions across that entire array. That's what vectorize does. So here, I've defined a function that actually computes over the entire array. So that's what NumPy does, is give you the ability to operate on arrays at a time. Move down. Next slide. It provides primarily an array object and then fast math. These are ufuncs, generalized ufuncs. You'll hear that word sometimes. These are operations, could be on single elements, could be on multiple elements, like addition. And it has some rules that help you combine two different arrays. Also has aggregations, things like you can do a sum across a dimension, a reduction of any kind, logical reduction, or usually sums or products. Move to the next slide. The key attributes are, you can see that it takes this big chunk of memory in one. It's really a linear chunk of memory. Memory is linear, single dimension in computer space, and according to the hardware, has this header information that says what data type it is and interprets every element of the array. And then there's shape information, which reshapes that data segment into a 2, 3, 4, 5 dimensional array. The key attributes are the type, the shape, number of dimensions, strides, and the data itself. That's all NumPy is. It's a collection that helps you think about a large array of data easily. Move on. Next slide. So examples, you can represent 2-dimensional array, 3-dimensional array. I like to think of 4, 5, 6. There's actually a hard-coded limit depending on how compiled. Sometimes 32. You can compile it to any limit. And conceptually, it shouldn't be a limit. It's just because of the way it's written. There's a couple of hard-coded static arrays in the C code. But effectively, it lets you do things like sum along a particular axis. You can take the mean, the standard deviation, just do quick calculations on all those data very, very fast. And those calculations take place in compiled code. So it's not slow. It's as fast as you can make the computer. Maybe happens on a GPU as well if you use CuPy, which is a NumPy version on the GPU. So move to the next slide. One of the powers is you can slice easily. Now, Python's list already has nice slicing with the step function slicing. That extends to NumPy in 2, 3, 4 dimensions by using a comma between the slicing syntax. And so you can do, grab a slice, grab a segment, grab with the strided slicing. That's the third argument to the slicing. The 2::2 and the ::2 example in green. You can actually get every other element. So it really has this rich ecosystem of ways to select data, just regular patterns of data. Anyway, you can pull that out very quickly. Move on. So this, NumPy was written to help Python be fast. Now, if you write Python with NumPy and you use arrays, you can actually do a lot of things very, very quickly. There's a whole, and this was known actually because of MATLAB and other languages. There's known as vectorized coding. This concept's been known for a while. If you actually have these arrays and write array code, you can do quick things very quickly in high-level languages. And so that's one reason. That's why Python started to dominate science, is because of numeric beforehand, then NumPy after NumPy unified numeric. When I came to Python, it was numeric. Great tool. Then move on, next slide. I know we're running out of time here. I only have a few more minutes, so maybe we can open up to questions before I go on to something else.
Okay, so there are actually some couple of questions. Okay, so the first question was.
Okay. Sorry, just want to say that if you have more time, we are okay to 20 more minutes. It's you can decide how many more minutes you're okay with sharing.
Right. Okay, excellent. I can probably do 15 more minutes, and then I need to go.
Okay, fine, you can continue.
Okay, so the first question was.
Yeah, go ahead.
Yeah, so besides contributing to GitHub repos, what other ways can someone join and contribute meaningfully to the Python ecosystem? Like, are they like official forum types, social types, communities, or like what ways can anybody join, contribute?
I'm not sure I understand the question. You're asking, can anybody contribute?
No, like someone's curious on what ways can they contribute to the Python ecosystem. So besides contributing to maybe code, besides contributing like on the GitHub repos, are there other ways they could contribute?
How do you contribute to a Python ecosystem? Is that the question?
No, yes, how can they contribute to the Python ecosystem besides contributing on the GitHub repos?
I don't understand the word you said. You said ACA contributions?
No.
I can say it because I'm the author of the question. Okay. So besides the GitHub repo or the repositories, besides going on all these different packages and repo and trying to contribute code and all, are there other ways one can be really involved with the community? You mentioned that people come to the language, they stay because of the community, and that's the greatest thing.
I see. How do you do that? How do you contribute to the community? How do you be a part of the community? Is it only making pull requests on GitHub projects? Is that the question? Kind of other ways?
Yes,
okay, yeah, great. Ways. Yeah, honestly, I think I saw the name of Vanessa here, who's been on the NumPy community as a contributor experience person, actually trying to help grow the contributor experience for NumPy. She's probably a better one to answer this question, but I can tell you some of my ideas or thoughts. One is the meetups, like things like this have been a great boon. We have PyData meetups all over the world, for example, and data science meetups. These are where the community gathers and where local communities thrive. So these gatherings actually become really significant. I would say, I bet 10% of the people that actually participate actually contribute regularly to some of the code. There are people who contribute a lot of code, and then there are people who contribute a lot of instructions, tutorials. Many people will maybe write Medium articles or LinkedIn posts, do YouTube videos, TikTok videos. There's a whole scientific Python ecosystem that's emerging where people, essentially just share their knowledge and their understanding with others. That's a great way to contribute. So you contribute to the ecosystem by sharing your understanding, and somebody else will resonate with that. So that's one way. Just there's multiple ways there. And to the GitHub repo, even if you're not going to contribute code, or let's say you're not going to write C code or Python code, there's tests and documentation that needs to be written. That can even start with a tutorial that's not even in the GitHub repo, that maybe is on a post you share. But getting it into the GitHub repo with the project means that it stays with the project and it has much more chance of being distributed globally and widely. So hopefully that helps. Maybe there's some other ideas.
Yes, mentioned some things. So thank you very much.
Okay,
Great.
so another question is okay. So I'm aware that the ecosystem of Python is evolving, and especially in Python APIs for machine learning operations. So the question is that, so how can they get involved in the package development? Like, he knows the guy, so according to, so he's good at programming and he loves the language of the packages and fundamental of programming, but it's a bit different. So how can he get involved with the code base of the package? How can he contribute and maybe probably build his own package as well?
How do I get involved in your package, or maybe another package?
Yes, or
Like how do
even the
start-
code base. Yeah. So how can he get started?
Yeah.
They...
Yeah, getting involved is usually a matter of just showing up, and sometimes doing kind of the work that other people aren't doing because maybe it's boring or not, they haven't done it. I mean, a lot of times going and maybe doing a release, like release management actually is a way I've seen people get involved pretty effectively. Release management means, okay, let's make a release. I'm willing to go through and curate the pull requests that would be part of it, write the release notes, create the tags, do the git work, the grunt work of releases. Writing tests is a great way to contribute to a project. Making a new project is also, if you have an idea of something that should exist, you can make a new project pretty easily. Just create a new GitHub repo and then start pointing people to it. It takes effort and a while to make it so that what you've produced is something people will want to download and use, but it's definitely doable. It just maybe takes, I think the one thing to realize about any new project is it will take you at least 18 months to 2 years for that project to really start to get traction. That's just because of human dynamics and the time scale of human adoption. You might get a few people getting it quickly in three months, but a lot of people, for them to really kind of start to use your package. Now, there are exceptions. Sometimes you have something that's pretty simple but really valuable that people just start to use immediately. And then maybe it's only 6 months, but it's still a time period. So you kind of have to think about, okay, if I start working on this, how am I going to be able to continue, at least to a degree, maybe at least once a week, contribute to this project so it doesn't disappear. Because communities take a long time to nurture and a long time to help. I've been really grateful for, a lot of times you'll do work with a community of people. You have to recognize there's people around you that have to carry it forward. I'm really grateful I've been able to build Quansight Labs. That's in the recent incarnation of my entrepreneurial work. The whole point of Quansight Labs is to give jobs to people working in Python data space. So we're finally able to support people working on NumPy and SciPy, which I wasn't able to do for 10 years, 12 years. So now finally be able to do that. And I want to do that more. I want to be able to allow for multiple open source research labs working on open source projects that help everybody. Every open source project that's in use should have something like that. And I'm trying to figure out how to make that happen and make that a phenomenon that always exists. Unfortunately, it only exists sometimes right now. So getting involved, patience, recognize that it does take time, and people have all kinds of things they're doing, and maybe they're volunteers as well. And so, patience, and then forgiveness. If it's easy to get your feelings hurt pretty quickly. Don't mean to be, but sometimes we're short with each other. Especially with text messages and really quick signals. So, having a space of understanding thinking people mean the best, and then really forgiving, and then putting effort into things is really what I can say is critical. Okay, any other questions? I'm happy to go on and talk a little more about Numba if people would like.
Yeah. So no, at the moment, it's not our questions. Then okay, no other questions.
Well, I thought I would talk about kind of. Oh, go ahead.
Okay, I'll be short about it. So Inessa2 has also put in some things in the chat, and so I will advise people to also go through it. So she mentioned how we can also join the NumPy. I think there's an event coming up soon. So she's putting details. So I think everyone should take advantage of it. So yes, please carry on.
How do I see that chat? How do you get to the chat?
So I don't know where your controls are, but for most of us, I'm also on Mac and it's up. So on the uppermost layer of the Teams window, as you look at my slides, there's chat, people, reactions, room. I hope you see that in yours. See those in yours.
Whew. I'm on a Mac and I don't see anything like that. Interesting.
Hi, Travis. Inessa is here. Can you see in your menu 3 dots?
I see 3 dots.
Okay, if you click on them, then you'll have a dropout menu and you'll see more options. One of them is a conversation.
Don't see the conversation option. I show device settings, show call details, enter full screen, show background effects, turn on live captions, keypad, turn off incoming video. That's all I see.
See everything we also see. So that means before the 3 dots, do you see some buttons beside the 3 dots?
I see a open share tray, a mute, and a turn camera off. Then a raise hand and a hide.
Maybe to the left.
People shots, reaction.
You're not seeing there. Okay, that's weird. It could be a glitch from Microsoft's end then. I can see reaction, I can see, okay. So someone is raising his hand. I don't know if it's for a question or just to draw attention.
Yeah.
I'm gonna have to load my Microsoft Teams. I'm gonna have something wrong with it. Weird.
It might be Microsoft Teams. Sorry about that. Okay, so we'll let you go on.
Oh, so yeah, Brian, I've muted you.
I think maybe because I cannot see it as well at my own side. Maybe because you joined through the web or something like that. Because I joined through the web, not using the app.
He joined from desktop, so maybe we'll let him go on so that I'm still controlling the slides. So just tell me when to move so that we can get a lot more from you before you have to go.
Yeah, just move on. So I want to talk about kind of how do people extend Python. That's kind of what I want, and I'll quickly talk about Numba, then I'll move on to some other folks. Numba, I really loved Numba because it helped me build what I wanted, which is for a long time, you notice back even when I was writing the routine to wrap QuadPack, which was an integration routine, it had to take a Python function, but the integration routine itself was in machine code. So it's going in, and one of the steps in machine code is to call the function. And at that point, it had to call back, if I just gave it a Python function, it had to call back to the Python interpreter. The Python function was executed in Python. So that became this real issue, like, oh, and then that caused me to think, all the way back then, how do I actually, could I write a function that would actually enable me to inject machine code in there, kind of a dynamic machine code function that then the integration routine could call? So it didn't have to come back and trampoline back and forth between native code and the interpreter code. Because that was actually one of the hard parts of writing QuadPack was actually handling that back and forth. Python calls machine code calls back to Python. How do you make sure, what if that Python call then goes back into machine code? There's like double entry problems. There's all kinds of questions that had to arise. All that got injected into a code called F2Py, which automatically wraps Fortran to Python. One of amazing tools that made Python easy to wrap, written by my friend Peter Peterson. But so for a long time, I wanted to say, what if we could just compile this? Then again, for NumPy, I just showed you an example of this vectorize idea. If I took a function in Python, but I want to take that Python express function and use it to apply it to every element of a NumPy array. Well, if I do that, and it's a Python function, then I have to call back into Python instead of just putting a native function that executes on every element of that NumPy array. So is there a way to create a compiler that would take Python code and compile it to native code, even if just for that purpose of writing functions that can call out to all these different pieces? So I wanted that for a long time. It was in 2012, finally, this LLVM library started to grow to the point that it was fairly straightforward to build a compiler that could compile Python code to native code. And again, so we wrote a Python compiler. It was kind of cool. It was a restricted one. That was the key. Lots of people have been trying to compile Python, but part of the challenge is Python's complicated. I didn't want to compile all of Python. I wanted to compile a subset so you could do kind of math equations. And so that's what we did with Numba. And it exists now. It's actually pretty well established. It's been around for 10 years. It's actually pretty far along. You can do a lot with it quickly. And the reason you can do a lot quickly is it builds on this wonderful tool called LLVM, which takes an intermediate representation of code and produces native code, produces x86, ARM, PTX means GPU code. So you can even compile to the GPU your Python function. And then it takes bytecode. So it just is basically a translator of the bytecode to native code. So pretty cool project. Move on to the next slide, actually. I think I'm talking about the next slide even, and we're not there. So it's using this LLVM backend, like I was saying. Go to the next slide. So with it, and this is just an example of how you might use it, you don't need to put in these type hints anymore, but at the time when I put this example together, you did. This just put type hints. The type hints are, okay, its image is going to be a floating point. It's a two-dimensional array of doubles of float 8-byte floats, and then the output is going to be there. And then JIT would just take that code, use the decorator. The decorator syntax in Python essentially lets you take a function and then call something and then return something. So JIT is like a function that takes a function. And what the JIT function does, it takes the filter function, looks at its bytecode, and completely produces a machine code version of that bytecode, and then a wrapper to call it from Python. So it kind of does this, right? Take a machine code, then put a wrapper in to call it to Python, and it replaces that function with the machine code version. And but it understands range in this for loops, and so you can basically do something like this, write it all in Python. And without the JIT, that would run, although very, very slowly. In fact, if you run it without the JIT, it's 1,500 times slower than if you run it with the JIT. Now that's a little bit of, it's actually because array scalars in NumPy are so slow. That's part of the reason it'd be slower than if you just did lists of lists, for example. But nonetheless, that was exciting. It was exciting to be able to write a compiler that lets you do 1000x speed up and still write Python code. So that's a really cool tool that's available to everybody right now. You can basically, if you have snippets of code, a little thing you want to make fast, you can see how to make a function, make it into a universal function across a NumPy array or across a pandas data frame, or you want to think about, I can do an image processing loop. Man, you write it in Python. It's pretty straightforward. A lot of people are doing that now. Move to the next slide. Let's move to the next slide. Talk about this. Simple ufunc. So this is an example of vectorize now, but now vectorize with Numba creates a machine code function that can just go really, really fast. So that's super helpful because while in NumPy I can write something like a times x plus b times y, that's cool. It also, if that's a big array, it creates a temporary copy. A times x produces a copy, b times y produces a copy, then I add them together, I have another copy. So I end up with these intermediate arrays. And the bigger they are, if they're only 1,000 elements like this, not a big deal. But if you have 1,000,000 elements and you're allocating memory, and that actually takes a long time. So you might have these slowdowns just due to temporaries. And so something like vectorize can make it super fast just to compute the underlying computation on the 4 arrays without creating any temporaries. Just select the items and produce a result very, very fast. And so Numba vectorize is really cool. And if we move on to the next slide, so that's one way to make Python fast too. Just use something like Numba vectorize. Then I actually went back and did a case study. So the Bessel function, the zeroth order Bessel function, was something I wrapped early on in something called SciPy Special. In 1999, I wrote a link between the Fortran library, the CFES library it was called, that produced the solution to this Bessel equation that's shown. These are solutions to this particular differential equation. You don't have to know about that too much, just to think of it as it's like a sinusoid, like a circular sinusoid. Move on to the next slide. So this exists already in SciPy Special, but I wanted to say, could I write this in Python? So here's all the code, basically, including the temporary arrays that are needed to basically compute this. And basically, it uses, if you look in J0, that p-value, it is a polynomial evaluation, polyval. It's a ratio. It does what's called a PyData approximation in most cases. So that PyData approximation uses these simple polynomials that were figured out long ago. There's different kinds of versions of it. But that is the code. And it's written in Python now. And you can kind of look at it and kind of, okay, I could change it, reevaluate it, do something different, figure it out. Using the vectorized algorithm, you don't have to use the type information anymore. It'll figure that for you. Move on to the next study. I could show, next slide, that became equivalent to the compiled code. So that version, the thing I just built really quickly, ended up being just the same speed as the accelerated code. But now it's in Python. Now you could actually target this GPU. You could run that on the GPU, much easier. All of a sudden, this language Python became, it's the syntax anyway, and these tools like Numba vectorize became a mechanism to bridge CPU and GPU land. Really exciting, actually. You can do some really cool things really quickly, particularly for rapid development and rapid iteration, which is, as I've said, is the key to innovation. So how do we make Python even more quick to iterate and innovate? So this is very exciting. I was very excited about this progress in this work. But still hasn't been done. I mean, you could, a few people have. I guess there's there's a few libraries out there that speed up certain algorithms in NumPy just using Numba, and you can get faster versions of things actually. So it's pretty interesting. Still emerging as kind of how to think about it. So move on to the next slide. I'm not going to talk about this, but there's a generalized ufunc, which you can also vectorize. That just gives you, when you have more than element by element, ufuncs work on elements. Generalized ufuncs works on dimensions. So you can take a whole dimension of an array, and so like a reduction, a reduce, I'm going to sum over an array, or a matrix multiply, for example, is an example of a generalized ufunc. But you can also produce those and create those for Python, for NumPy. This is an area where NumPy could be better. The generalized ufunc support is there, but it's not as clean as it could be. Move to the next one. Move on to the next one. This is an example of just different kinds of functions. Keep going. Keep going. Next one. Okay, so I want to read a DICOM format, and I produced in a function of something called NumPy.io. I'm going to quickly go through some slides here just to give you an idea of how did somebody like me actually extend Python with a C code. Now, if you don't know C, this will go over your head, but I wanted to illustrate for those that do know that it's actually accessible. It's not crazy. And actually, I wanted to point out, go to the next slide, that I used an example from Michael Miller called NumPy.io to start my journey. There's actually a pretty good example out there from my friend Elon Schnell, who I've worked with for a decade now. He built all the first versions of Anaconda itself. He has an efficient array of Boolean library called BitArray. And what I like about BitArray, it's a very simple library. If you don't need bit fields, they're not useful for you personally, but it's a very good example of how to extend Python. Very clean code, very simple, not a lot of extra fluff. And so you can very clearly see, oh, if you just cut and paste BitArray and replace the functions with ones you want to call, you can probably build your own extension module pretty quickly. So go to the next one, and you can see BitArray, and that's what I did. I actually made my first extension module by cut and paste programming, copying table.io from somebody else, from Michael Miller. That's how I built something called NumPy.io to begin with. So that's how I got my journey started. So I highly recommend cut and paste programming. You don't have to, a clean sheet of paper is hard to innovate with, but go grab somebody else's and start tweaking. That's how the internet was built as well. Everyone copied each other's web pages. So do not hesitate to go and And yeah, I know when you grow up, they call that plagiarism, but as long as you give credit, as long as you say, yeah, I got this from this person, it's fine. And that's the power of open source. So this is the Python level. You have a class, bit array, these different functions, so forth. Go to the next slide. And this is the C level, right? At C, you have a module def, which is a static object that has this, it's just a data structure, which has the module functions. The module functions is a function table. If you look at it, it's just itself another data structure with a string, a function to call, and kind of some, how is it going to be called? What arguments are going to be called? And the doc string. That's it. You sort of have these module functions that are now available in bit array. Things like bit diff and bits to bytes, those are now functions that are going to be called. And if you look at these, example sysinfo, that sysinfo function, what it looks like is just this, returns a PyObject star. Everything in Python is a PyObject star, a pointer to a Python object. That's kind of what the C level sees it as, a pointer to a Python object. A Python object itself, what does it have? It has type information, and it has a reference count. Those are the two things it always has to have. And then it has maybe some data allocated. You can see in this case, the bit array, in the module initialization, does some initialization. When you load bit array, what does it do? And that's pretty much all you have to have in order to create a bit array. Now go to the next slide. Bit array also adds a new type, a new built-in type, like a NumPy array. Oh, here's the Python function in C. This is what a Python function in C looks like. The PyObject star self is always there. The argument's actually passed in the V, in PyObject star V, and the return is the PyObject star as well. And you look at what happens to V in that code. Well, maybe you can't read C code, but you can kind of look at it and say, okay, if it's not index is a macro that says, is this an integer, basically, a variable that could be used as an index array, as an indexer. And if it's not, then it raises an error, just like that, pair set string, the type of error, and then return null. That's what you do from C to tell Python an error was raised. You return this null, the 0, basically. Otherwise, you use this getIndex function, and you have to look what the getIndex does. GetIndex basically takes the value from V, the actual value in V is an object, remember, and pulls it into an actual C integer. You can see that n is now an integer. And then it looks at that as if it's not positive, then it returns an error. Otherwise, it returns a Python integer. And that's a Python function in C. It's a little more complicated. You have to have these cast functions. You're dealing with the raw bytes and raw bits. You have to worry about exception handling, but that's how you do it. Go to the next slide. Next slide. Yeah, this is what's necessary to create a new type in Python, like a class. A NumPy array is just one of these. A NumPy array is a big static object which has a bunch of function pointers that do things that Python is expecting. Like, what happens when I print this? What happens when I convert this to a string? What happens when I call the getAttribute method on this object? And you basically have to have a method. You have to have a function that implements that, and it can be written in C. And there's more details you can read about this, but that's what you start to learn about this, and you start to, oh, I can create anything I want. And you can. Python's extremely extensible. Move on to the next slide. And these are all the methods you then put on. Next slide. And they're very similar to the other kinds of other object files we talked about. Okay, and then, well, this is actually the object itself. And you can say here, all Python objects look like this. There's a head, then maybe other things, and then the head, the PyObject var head basically has the type information and the reference count. Every PyObject star has those. In fact, PyObject star just defines those variables. Now, bit array object defines all these other things. There's more data in there, and you can see it depends on the object you're building as to what data you want to put there. And that's how you create extension objects in Python. All right, next slide. So hugely powerful. That's what NumPy did. That's what I did with NumPy. It's what I did with numeric. Everything. That's what pandas can do that too. In fact, we did it a little differerly, but you can build everything. Now the challenge is reference counting. You have to do it manually. Nobody's taking care of that for you. You have to do it. Otherwise, you'll have memory leaks. Error handling. You have to do it. It can be tedious. And then initialization. You have to be careful about making sure that you don't reference memory that's not yours. You can actually cause segmentation faults and other issues. The other problem, the big problem, is other runtimes, SciPy, Rust, Python, WebAssembly. It's harder to use your tool. Now, WebAssembly is getting easier these days to use your tool, even if you write a C extension. But others, it's been hard. PyPy, that's one of its biggest problems. PyPy, if you don't know that project, it was a Python compiled Python. Really interesting project, super brilliant people writing it. But they couldn't reach critical mass because the Python community uses all these extension libraries. And PyPy couldn't create them, couldn't bring them over very quickly. They didn't work with PyPy the same way. They weren't as fast. They were too slow. Anyway, so it became really difficult. But this extension capability is what makes Python incredibly fast. And everything's available to you. Multi-threaded, GPUs, like nothing holds you back. This is why Python took over, because the extensibility of Python enabled people to write extensions. So the adage of, use a better algorithm, hopefully somebody else wrote, could be applied to Python. And then that continues to go, continues to carry forward. Now there's some, Numba's emerged, a simple way to write extension code without having to learn all this. And then finally, I'll end by showing a couple things. Then I gotta go. Show a couple of examples. Move on to the next slide. Cython. I'll just end by pointing out Cython. Cython is a really cool tool, and it's a tool that lets you write Python syntax, and especially with type annotations, there's a way to not use. I would recommend not using any of the special Cython syntax that is available. You'll read about it online. Don't use that. Use Python syntax, and then you can basically, it'll automatically compile an extension for you. So you don't have to learn any of that C code. You can just write the high-level Python code, and then you'll get an extension out of it. And so it's pretty cool, actually, what it enables. And it enables a lot of, in fact, pandas, a lot of scikit-learn, a lot of libraries have been written using Cython. Cython came out about, late or 2007 timeframe, 2008 timeframe. So excellent. So there's a couple more slides here that go into detail about Cython, but really I don't have time to go into them. And so I'll have to leave it right there and just say, that's what makes Python extensibility, and the cool tools around it have made Python take over the world. So it's going to be great to be here and visit with you, and I'm happy to get to know more of you. Always excited to meet people. And like I said, OpenTeams is looking for architects, and then OpenTeams Global is looking for talented people who we can put into projects all over the world. So if anybody is looking for opportunities, please reach out. It's not every opportunity is maybe the right fit for you, but we're always eager to talk and build our network. Any final questions before I take off?
Thanks a lot. Gabriel, your hand is up, so you can quickly speak.
No, I don't. I was clapping.
Oh, okay, great. So just 2 questions. I know you have to go. You've even been generous with your time. And so can you maybe just tell us about, you combine the 2 questions. So the 2 questions are, one is your journey, you told us some of it, but maybe if you tell us in a more personal way, how you actually started, maybe, I don't know, from your mom's womb, or whenever you decided that, when you said that this was going to be the path you would take, and because it looked like you made a decision that was the path. We would like to know how you came to that discovery of this is the path. And then the second one is your advice for we, the younger guys. When I say younger guys, people just trying to figure out their career path right now, but I'm finding this very interesting, and how we can stay on the course, and hopefully as long as you've done in whatever new tools become the one ready to the future.
Those are good questions. I would say I did not know that. Like, that's the hard part, is your life is taking steps into the dark, but meaningful steps using the best information you have. So every time I've acted out of passion and a desire to do something, not to further my career, not to make myself more money, not to do something like that, not something very personal. I've acted in a way to serve others. I've acted in a way that I feel like helps other people, and is something like, when I wrote NumPy, it was actually not a great thing for me to do, because I had to, my career as a professor my bosses were telling me to do less with open source. They're saying, write more grants and get more papers written to make my career better. And so, but I saw that there was a need to unify the array communities, and that there was nobody else out there who had enough knowledge to do it. And so it kind of was, I felt duty bound. And so I knew that it would put my career at risk, and it did. I didn't get tenure at my university because I focused on NumPy. But I still felt like I knew that people needed it, and I wanted to serve them. So I would say, as you're exploring what you're doing, think about who you're helping. Think about the people you're helping and the work you're doing to help them, and focus on that first, and then the rest will come. The rest will come to you. So and what the rest is, I don't know what it'll be. And it doesn't mean that everything's rosy. Tough times happen. I had to leave my job. I didn't get tenure, right? And so I had to find a new career. So it's not like everything's been easy. Starting a company, trying to get funding, none of that's gone simple. But every time I've taken action, I've tried to act to help others. That's probably one thing I'd say, and that's been real. That's kind of a personal view of mine, but it's one that's I can resonate with and say has really helped. Getting started's hard because most of the things you do aren't necessarily going to work. I've done a lot of things in my life. Some things haven't worked. I tried the XND as an example, Blaze. These are things I've tried to do that didn't work. And so I understand, that not everything works, not everything succeeds. And so you try to understand why, what the issues are, and see if you can't make steps to improve those issues. You learn from every experience. So I would say, keep going. Don't get discouraged. Keep moving. And if you're moving in a direction that drives with things you're interested in, be interested. So I wrote Numba because I wanted vectorized. I didn't necessarily want to have a compiler of Python. I wanted vectorize. And so, I had to get a compiler to get vectorize. So, I would say be driven by user stories, use cases that matter to you, and keep focused on service. Hopefully that helps.
Yes. Thank you very, very much. I think at this time, we have to also reciprocate your generosity and say thank you and let you go. I know Inessa has some things to say to us, so maybe she can carry on from where you stop and tell us what she wants to say.
Yeah, listen, Inessa has a lot of ideas, and so it's great to hear from her. Inessa, I'm going to say goodbye. I've got to run. I'm going to miss my wife's time.
Thank you.
So,
Thank you very, very much.
Let's see some of you again. Bye.
Thank you, guys.
Hi, everyone. Can you hear me?
Yeah. Very clearly, yes.
Yeah.
Listening to Travis reminded me that all great leaders are excellent presenters and educators. I must say this was completely uncoordinated. I just stumbled on this event on Meetup. I run some groups in the region where I currently live in Southwest Florida, and I thought to join after seeing Travis and Benny being part of this event. I've really enjoyed the presentation and learned something that I didn't know about NumPy, even though I've been with the project for over 3 years now. Yes, so I started as a contributor, as a volunteer contributor to NumPy in mid-2019, and last December I stepped into my current role, which is a contributor experience lead. And a little more about my role, I guess. I'm responsible for onboarding and supporting contributors. Benny was one of the contributors that joined NumPy in early March, I believe. I'm also revising and introducing policies to address identified gaps in the project governance, and also developing programs to diversify pathways of contribution to the project. I really appreciated the question that somebody posed, what you can do beyond submitting code patches. And
I know you shared some practical ways. I know you gave us, like, was it an event you said is coming up?
yes.
Is it something we can join for free? And also, is there a way we can apply to also be contributors, on since you say you recruit contributors, so how can people in here in this meeting right now take actions beyond what we've heard and say, oh, I'm also going to join and I'm going to follow the link or register for the event in essence, share the details of. So which ones do you want to share with us as links and events that we can register for?
Thank you for the question. We host what we call community outreach events, and one is coming up on the 2nd of December, so this Friday. It will be hosted between 2 to 8 p.m. UTC, which should be very convenient for those of you who are in Asia and Africa. I will share this. So I must say the announcement about the NumPy newcomer sprint hasn't been made public yet. I will share this information with the organizers of today's event after the event, if you don't mind, but I'll tell you a few words. I will share a few words about what newcomer sprint is. And I strongly encourage you to join, if not a sprint hosted this Friday, sometime in the future. This is an event, a safe space to learn more about the project and also learn how you can contribute. Meet some of our maintainers who would guide you through a problem that you choose to work on. And we decidedly choose issues that are fairly easy to solve for newcomers. I must say NumPy is a pretty complex project. It's a mature project in the life cycle of open source projects. As Travis mentioned, it was the first release happened in 2006. But if you want to contribute to NumPy, joining a newcomer sprint is one of the best ways to start contributing to the code base. And now, as I mentioned in my message in the chat, contributing code patches is not the only way to contribute to NumPy. I'm actively working on diversifying pathways of contribution. Just like every organization that is successful, there are many needs besides writing code. The current needs of NumPy beyond code are triaging issues, developing educational material. We also have a website, numpy.org, that requires maintenance, and I'm happy to talk about that. Also, if you have some skills in graphic design, or you know someone who is a graphic designer would like to join the open source movement, we have quite a few projects, sub-projects that we would like to implement. Also, I noticed that some of you are not English native speakers, and for those of you who are wondering about my background, because as you can tell, I don't have an American accent. I'm originally from Ukraine. So we are trying to bring NumPy outside of English-speaking countries, and we are slowly building a translations team. So translating and localizing content is something that would be of great value if that's what you're interested to do. I would say this is pretty much all when it comes to current NumPy needs. And yes, if you have any other questions about contributing to NumPy, please reach out to me on Twitter.
Okay, on Twitter, that's what I wanted to ask. How can we reach you? Okay, so I'm sure Ifeanyi will share your Twitter handle, so he knows the easiest way to reach everyone. So I'm going to say a very big thank you. Ifeanyi, sorry I've hijacked your session. I think we can close. Do you want to wrap up the whole thing?
You can close the session. I'm showing the Twitter handle right now. So this is Twitter handle. This is our Twitter handle.
Okay, great. So thank you to everyone. Thank you, Inessa. Thank you also to Travis. I know he's out to go. And to everyone who has joined too, a very big thank you for making it and staying this long. There's another session in about 20 minutes, but we can always share that in the chat. So whoever is interested will join. It's about Power BI. But I want to say a very big thank you to you all and have a wonderful week ahead. Thank you, Inessa, and everybody, people I know, people I don't know. I see a lot of regular faces. I say thank you for joining. Bye. And thank you, Matt Bones. I hope I pronounced correctly. I liked the question you asked, and I took some learnings from it too. So thank you to everyone. Bye. Bye. So
My pleasure. Bye bye.
So okay, so always ask for the Power